Our galaxy isn't just expanding with the universe, it has extra motion layered on top. Nearby galaxy groups share a subtle drift, as if our whole neighborhood is sliding downhill in space. The name, Great Attractor, makes it sound like a single monster, but that's the trap. What we're really chasing is a gravitational fingerprint, motion that points to mass we can't fully see. Tonight, we map the pull using the only witness that can't lie, velocity. The universe expands, so galaxies generally move away from us with distance. But peculiar velocity is the extra component, the deviation from pure expansion caused by gravity. If many galaxies show a coherent residual flow, it implies a mass distribution steering them. The Great Attractor is inferred from those residuals, not photographed directly. In this case file, motion is the evidence. The most suspicious direction lies close to the Milky Way's plane, exactly where dust and star crowding block optical views. Astronomers call it the zone of avoidance, and it's a genuine observational blind spot. So the strongest pull seems to come from behind our own galaxy's curtain. That's why the Great Attractor has always been part science and part visibility problem. When visible light fails, astronomers switch wavelengths. Infrared surveys can see through much of the dust, and radio observations can trace neutral hydrogen in obscured galaxies. These methods don't solve the zone of avoidance, but they reduce the unknowns. Every newly detected galaxy behind the Milky Way is a new data point in the gravity map. The curtain is thinning, slowly. One heavyweight in this region is the Norma Cluster, Abell 3627, often discussed as a major mass concentration near the Great Attractor direction. Its cluster-scale gravity, not a single galaxy, and its location behind heavy foreground clutter makes it notoriously difficult to characterize. Distance and peculiar velocity work on Norma matters because it tests whether it's a true core of the basin or just one contributor in a larger landscape. The deeper we measure, the less the story looks like one object. Gravity on these scales behaves like topography. Clusters and filaments create valleys, voids create ridges and slopes. The Great Attractor is better understood as a basin-shaped region in that terrain, not a pin on a map. That's why early descriptions felt mysterious. People wanted a single target. The universe offered a gravitational landscape instead. Farther out, the Shapley Concentration enters the story, one of the most massive nearby overdensities known. On larger scales, Shapley can contribute significantly to bulk flows and may account for part of what the Great Attractor label originally tried to summarize. This is the twist. The pull may be layered, local basin plus deeper, more distant gravity. The suspect list expands with distance. In 2014, a major approach reframed the entire narrative, defined superclusters by flow basins, like watersheds. Using peculiar velocity maps, researchers outlined a volume where galaxy motions converge, our home basin, called Laniakea. In that framework, the Great Attractor sits near a convergence region inside the basin. It wasn't just something pulling us. It became the drainage system of our neighborhood. Peculiar velocity requires real distance, not just redshift. That means distance indicators. For spirals, relations that tie rotation to luminosity. For ellipticals and clusters, scaling relations like the fundamental plane. It's meticulous work, calibration, corrections, and uncertainties, because small distance errors can mimic false flows. This is why mapping the pull is slow science. You're measuring gravity through measurement discipline. Modern reconstructions rely on large peculiar velocity catalogs such as the Cosmic Flows program. These datasets stitch together thousands of distance measurements to recover a coherent velocity field. But the field is noisy and incomplete, especially near the zone of avoidance. So astronomers don't just plot points, they reconstruct the most probable flow that explains them. The map is a statistical portrait of gravity. One widely used technique is Wiener filtering, a method that estimates a smooth large-scale flow from incomplete, noisy data. It's not imagination, it's constrained reconstruction. The solution must fit what's observed while remaining physically plausible. Where data is dense, the map becomes sharp. Where the sky is blocked, uncertainty grows. That uncertainty is part of the mystery, because the blind spots are real. Then came a counterintuitive idea: flows aren't only pulled by overdensities, they're also shaped by underdensities. A large void can act like a repeller in flow reconstructions because matter accelerates away from emptiness toward denser structures. In this picture, local motion can be described by a push from a void and a pull toward major mass concentrations. The Great Attractor story becomes two-handed: attraction plus evacuation. Even with modern surveys, the hardest region remains the one behind our own galaxy. Missing redshifts, uncertain distances, and survey gaps create holes in the reconstruction. And small gaps matter, because flows are sensitive to total mass, including dark matter. This is why the phrase, "still can't fully map," is honest, not dramatic. The limitation is observational geometry. Light traces mass imperfectly. Much of the gravitational budget is dark matter, invisible except through its pull. Two regions can look similar in starlight yet differ greatly in total mass. That's why flow mapping is powerful. It responds to total gravity, not just what shines. The Great Attractor is ultimately a mass distribution problem, not a brightness problem. The phrase, "the Great Attractor," suggests a single destination, but flow basins can be nested. Local convergence, regional convergence, and supercluster scale convergence are not always the same point. Boundaries behave like watersheds, cross one ridge and galaxies drain toward a different basin. So asking, "what are we falling into?" depends on scale. The universe answers with layers, not one dot. The simplest honest answer is, galaxy flows are responding to a combined gravitational field. Locally, a basin near the Great Attractor direction, fed by clusters like Norma, helps shape our neighborhood's motion. On larger scales, Shapley becomes a dominant influence, while voids on the opposite side contribute a push. The net flow is a vector sum written by the cosmic web. Not one hook, an entire geometry. A solved Great Attractor story would look like a dense, all-sky gravitational atlas. It would include better distance coverage behind the Milky Way, deeper redshift completeness in obscured regions, and tighter statistical reconstructions. With each improvement, the basin boundaries sharpen and the contribution of each structure becomes measurable. But the better we map, the more we see the hierarchy of flows. The mystery doesn't vanish, it becomes a map. The Great Attractor isn't a paranormal force. It's gravity revealing where mass really sits, and where we're still blind. Our galaxy blocks the view, dark matter hides in plain sight, and measurements carry uncertainty. Yet the flow signal is real, and it's consistent with a cosmic web of basins, ridges, and voids. The universe is not pulling us toward one secret object, it's moving us through its full structure. So what are galaxy flows being pulled toward? A partially hidden basin in our local neighborhood, shaped by massive clusters and filaments, and linked to even larger structures like Shapley, while voids push from the other side. We can map the motion with increasing precision, but parts of the source still sit behind the Milky Way's curtain. If it sounds impossible, we investigate it. Subscribe, and join the next case.